So on Monday, we actually have the introduction, a brief introduction about the California bearing ratio test, which is the standard H2 T193. And you also, some students have already conducted the experiment. I mean, today and yesterday. You have the experience about how to prepare the sample and how to operate the machine to record the data. And of course, you have already received the data, or you have downloaded data from the experiment. And the next step you have to do is finding the CBR, the California bearing ratio, for the sample that you prepared. And basically, we want to find out the CBR with the equation that is defined in this formula. It's the load carried by the specimen at 0.1 inch penetration rate, penetration. And if you divide it by the load carried by the standard crushed rock base. So this is actually in the percentage. It varies between 0 and 100. That's the common value for the CBR. And with your experiment, you should also find out the value, which will be around between 0 and 100. And in this equation, you will also see that the value at the bottom is the constant, which is 100 psi and 600 and 6900 kilopascal. So that's the basic way for you to calculate the CBR value. But regarding to the data analysis, we still need to have some further process about the raw data you collect from the experiment. Generally, from the experiment, you can find out a data set which will be quite similar to this table. There will be two columns. One column will show the penetration, which is the penetration you applied at a different load. And the other one is the pressure, which is the pressure applied to the sample. So you can find out the penetration at different wait a moment, let me try to stop timing. So you can find out the pressure at each penetration. And what you need to find is the penetration, it's the pressure or the load at 0.1 inch, and divide the value with the standard value, which is 1000 psi or 6900 kilopascal. And the next thing you will need to think about is how to process the raw data. If there's any error that you have conducted, how you're going to correct it. Actually, it's very common for you to find out some error in the data in the raw data you collect. So usually for the CBR test, we need to apply the correction for us to find out the exact value of the load at penetration of 0.1 inch. So in this figure, you will see how we will do the correction. Basically, you can see that when in this figure, the blue triangle will be the raw data that you collect from the experiment, and ideally, at the low pressure, there should exist a linear relationship between the pressure and the penetration. But what you observed in the raw data, which would be the blue line, the blue triangle in this figure, it's actually having a convex relationship at the beginning. So this is what you will observe, a convex relationship at the beginning. This does not quite make sense. We want to find out a correction to remove this convex relationship, and usually this kind of relationship is caused by the inappropriate compaction of the sample, all the way for you to level the sample surface, or it may caused by the mode, the actual weight you apply to the surface of the sample. And in order to remove that kind of error, we will apply a linear relationship to fit to the observed points, and then we will try to find out the offset and use this offset, which would be the crossing, the interaction between the line, the fitted line with respect to the horizontal axis. Apply this offset to remove to shift the observed data from its original position to the left. Make sure that we have the linear relationship at the beginning. So the way for us to do it is like there are actually some standard way for us to find out the fitted line. This figure actually shows one example about the Sawyer LM3. It's actually from the solved experiment, but it's also applied to the unsolved experiment. So we have a set of the data. So this one, these two columns would be the raw data you observed from the experiment, and you can draw the curve, which would be the blue line as shown in this figure. And now the first thing you have to do is like you need to find out draw on a line which will tangent to the measured curve at the point of the inflection with the highest slope. So this is the very critical point. So you need to find out the curve which will be tangent to this to the observed or the measured data, and the line will tangent to the curve at the point with the highest slope. And next, you need to find out the interaction. Say that this value is around, I don't know the exact number, it's around 0.04. So you want to find out this interaction between the line, the fitted line, and using the fitted line and the horizontal curve to find out the interaction. And then what you need to do is that you need to subtract the original or subtract the observation to the intersect of the fitted line and the horizontal axis. So what you need to do is that you need to for all the values for the first one, you have the penetration around 0.000, which is 0. You need to minus 0.04, which is minus 0.04. And then this one, the second one, is also need to subtract from the 0.04, which will give you the value as 0.0115. And the next one would be 0.1 and so what do we get is 0.35 and so on. So you will have those points. This would be the adjusted points. Or definitely, if you see any negative points, you must remove them. It does not make sense for your analysis. And then what you need to do is like you need to sorry, this should be 0.01 and 0.035. And then you will have the values for the other points, just subtract them. And of course you will have you can find out the pressure. The pressure it does not change. The pressure is still the same to all the data points that you observed. And now you put use the pressure and the adjusted penetration to draw a new line, which would be the pink line in this figure. And this one is called the corrected CBR curve. And what you need to do is like need to find out the value of the the value of the load at or the pressure at the penetration of 0.1 inch. So with that, you have the value around. You have to use the pink curve. So the value is around. I cannot get that one, but in this case, you get the value as 1481.6 psi, and you can then calculate the CBR. The CBR will be the value that you observed, 1481.6 divided by 1000 psi. So in this case, this is a this is actually in the real case. Usually we have the CBR between 0 and 100, but this case, this is in a specific soil material. So you have the value at 148.2, which is the value here. So it's a higher than 100. This is not quite common, but we can observe this kind of result in reality. And for most of the experiment you conducted in the lab, it was between 0 and 100. So that's the way for you to conduct the CBR correction. This is also the most difficult part for you to understand or for you to analyze the data in the CBR test. Do you have any questions so far about the CBR test?
Doctor, sorry, how do we get the adjacent penetration, the last column?
The last column. So this is not adjacent; it's adjusted penetration. So you need to use the you need to use this tangent line, and the line should be tangent to the measured curve, which would be the blue line at the highest slope. So this would be the point of the inflection at the highest slope, and this red dashed line should intersect with the horizontal curve, and the intersection is actually the value you want to record, which in this case is 0.04. For this example, 0.04. So the adjusted penetration is actually the penetration minus 0.04. Well, this is the intersect that you observe from your correction. So with that, you shift all these points. You actually shift all these points to the left about the value of 0.04 for all the observed data points. Well, as we are only care about the value around 0.1 inch, so originally we only calculate these 4 values, but you can actually calculate all the other values. Like for this one, 0.16, and this one is 0.26, something like that. And then you will have the pink line. That will be the corrected CBR curve. You will need to find out the load or the pressure under 0.1 inches from the corrected curve. Okay.
Yeah, okay, thank you.
Okay. So you need to, in your lab experiment or actually for all your analysis about the problem related to the CBR test, homework and lab experiment, you all need to conduct this kind of correction. And your result may be different because you may have different line to fit the observed curve, but the CBR value should be quite similar to each other. Okay. Any other questions? If no, I will just jump to the next topic. Okay. Okay. So the next one, we're gonna try to use the CBR to evaluate the property of the soil. Generally, if the CBR is higher than 70, we say that the soil has a very high quality, and this will be applied to the soil type A1 from the H2 method, or GW, SW, GP, and GM for the USCS classification. And if it's between 20 to 70, we say that it's good. If it's between 5 to 20, it's weak. And if it's less than 5, it will be very weak. And usually that will be the A6 to A7 type of the soil, or the clay or silty soils. This kind of soil will not be appropriate for the subgrade. So that's the very rough classification to identify the quality of the soil based on the CBR values. And we can, if we do some empirical analysis, we can also find out the relationship between the resilient modulus and the CBR for the subgrade soil. There will be some. There will be a lot of studies about this relationship, and they can use some statistical models to find out this relationship. Just a moment. Okay, sorry, just exited the meeting a little while. So basically, we can find out the resilient modulus is in a function of the CBR. There will be two. Well, these two models are quite equivalent to each other. If we are considering the MR with the unit of the megapascal, then we can get an MR equal to 17.6 times CBR to the power of 0.64. Or you can find out in the simplified model where it's a linear relationship between the CBR and the resilient modulus. That is 10.3 times CBR. If we are using the unit of PSI, then you will have MR equal to 2555 times CBR to the power of 0.64, and this one is equivalent to 1500 times CBR. So we have the linear relationship, and this is actually it's only applied for the coarse material. It's a clean, non-plastic material with the CBR less than 100. If it's higher than 100, then this model does not able to describe the relationship between CBR and MR. And also you have to remember that this is just an empirical model. It's not a physical relationship. So it might vary based on the type of the soils. So the figure here actually shows the two type of the lines. One is from the line with the CBR to the power of 0.64. The other one is using the linear relationship. So the pink line is the nonlinear relationship, and the blue would be the linear relationship. And again, this is just an empirical example, and it does not show the physical features. And we also have some other models. The one that we showed in the previous page is the H2 study, and we also have the CSIR, which will show the relationship of MR as the 20.7 times CBR to the power of 0.65. These two are quite similar to each other. They only have a certain difference in the coefficients. For the power of CBR, they were even very close to each other, 0.64 to 0.65. But for the coefficients, it's a little bit different. Basically, the CSIR can use the CBR to measure the larger resilient modulus. And also, they have the U.S. Army Corps of Engineers model. It's also applied a similar format about the relationship between MR and CBR. It says that MR equal to 37.3 times CBR to the power 0.71. In UK, we also have the model, a linear model for the clays, which is quite similar to the Ashton, the linear model from the Ashton. They say that MR equal to 10.3 times CBR, but this is only applied to the fine-grained soil and fine sands with the CBR less than 20. If the value CBR is larger than 20, such as some coarse materials or for some of the granular materials, then we cannot apply this linear relationship. And the coefficient is not a constant, as see that it could change it with respect to different type of the soils. Basically, the coefficient may vary between 5 and 20. And with all these models, we do some summary about all these models, and generally find that there isn't a function to describe the relationship between MR divided by CBR and the features of all the load applied to the soil, including the bulk stress, divator stress, and moisture contents, and so on. So the figure on the left shows the distribution of the MR divided by CBR. And you can see that the mean value is around 4.38, and the standard deviation is 2.70. And this actually indicates that the what kind of range of the values we can use for the linear model to show the relationship between MR and CBR. And the second one is about it shows the distribution of the MR divided by CBR to the power of 0.64, and it has the mean of 30 and the standard deviation of 14.12. And again, it's similar to the left one, but this one shows how what the coefficients we can use for the nonlinear model to describe MR and the CBR relationship. And of course, as I mentioned previously, the moisture content has a significant impact to the properties, to the soil properties, including the resilient modulus and the CBR. It will also affect the relationship between MR and the CBR. In generally, we can see that with a higher moisture contents, which would be the those three different type of the dots in the figure. Red means the moisture content of 2.6% does not contain a large amount of the water, and the diamond represent the moisture content of 4.6, and the triangle would be the value of 6.6%. So basically, you can see that with a higher moisture contents, the MR divided by CBR values would be smaller. Also, if you go to check the bulk stress, with for different, if you are considering the constant moisture contents, by increasing the bulk stress, which means that you will apply higher load to the sample or to the pavement structure, the MR to the CBR value, the ratio would be larger. And this means that this relationship is also related to the traffic conditions or the loading values to the pavement structure. And here we also have some empirical results about the value of CBR and the coefficient of subgrade reaction K. So, and we can also show the relationship to the resilient modulus. And with the resistant value of with the modulus of the subgrade reaction K, you can find out the different values of the CBR value, different CBR values. For example, for this, for k equal to 200, generally represent the CBR around 10%. If it's 300, that will be just some value a little bit higher than 25. So this one shows the relationship between CBR and the modulus of the subgrid reaction from the empirical data. And and this table actually shows some recommended value for the modulus of the subgrid reaction for different type of the soils. And also you can find out the recommended value of the CBR. Basically for A1, A1A well graded soil, the K value will be 300 to 450 psi per inch, and the CBR would be 60 to 80. You can find out the values for the other type of the soils defined by the S2 method, or you can find out the CBR and the K values for the USCS classification. So with that, we can make a quick summary about the CBR ratio test. And this test is very important. It can help us to classify and evaluate the soil subgrade and base course materials for the flexible pavements. So this is one important application, but it's mainly applied for the flexible pavement. And we will also know that this kind of test is empirical. It's not the physical. It's not the physical features of the material. This one is quite similar to the resilient modulus. It's also an empirical analysis. And the result cannot be accurately related to any fundamental properties of the material. So that's what we can conclude from the CBR test. Any questions so far about the CBR test? Okay. If not, then I will go to introduce the last feature for the to understand the reaction of the soil with respect to the shear stress. And usually this one is very important for us to understand how the pavement structure will react to the shear force and what kind of severity of the slippage that you will observe on the pavement structure. You might have, if you already attended the first tutorial, you might have some sense about different type of the distresses applied to the pavement structure. While the important distress is slippage, and it's usually caused by, usually occurs at the some location close just in the front of the intersection, caused by the deceleration or acceleration of the vehicles. And this kind of behavior, deceleration, acceleration behavior, will generate a very large shear force to the pavement structure. And if the pavement material does not design appropriately to support this shear force, then it will cause some failure, and it will observe this slippage distress. And as the designer, we need to understand what's the shear stress that one material that we select can support. And we want to identify the standard procedure to measure the impact of the shear stress to the soil. So the triaxial compression test is then introduced to measure the impact of the shear stress. And of course, we want to do this experiment under the controlled drainage conditions and with certain moisture contents. And the setting of the triaxial compression test is very similar to the resilient modulus test. They will actually apply the same machine to do the experiment. Basically, we will prepare the sample and then put the sample in the cylinder, and we will then import some of the fluids or the air pressure in the cylinder to the sample, and then load the apply some axial load to the sample. But different from the resilient modulus test, where in the resilient modulus test we will have the repeated load. We will apply load and then decrease, and then apply the load again. We will repeat this on for hundreds and thousands times. While for the triaxial compression test, we will apply constantly increase the load until the sample fails in the test, which means that you will see the significant deformation of the sample, as you can see in this figure. So the analysis about the stress and strain of the triaxial compression test to the sample, to the design sample, it's very similar to the resilient modulus test. In that kind of test, in the triaxial compression test, we want to identify the shear stress, but we can actually apply the Mohr circle to estimate the shear stress through the principal stress. So with the design of the triaxial compression test, we can actually find out the major principal stress, intermediate principal stress, and minor principal stress, which would be the sigma 1, sigma 2, and sigma 3 applied to the sample. Basically, as the sample is in the cylinder, and we applied the constant air pressure or the liquid pressure to the sample. So the intermediate principal stress sigma 2 will be the same to the minor principal stress sigma 3, and this is actually one good feature that we can utilize. And in the for the major principal stress, it will actually be consist of two components. One is the stress applied from the machine. That is the applied axial stress, which we define as delta sigma. And the other one is the confining stress, which is the stress from the air or from the liquid. That is sigma 3. So the major principal stress, sigma 1, is a delta sigma plus the sigma 3. And here, delta sigma, we can also call delta sigma as the deviator stress, as what we defined in the resilient modulus test. So that is a deviator stress. So in the triaxial compression test, we will actually try to load the sample to failure under 3 different confining pressure. That is 15, 30, and 45 psi. This kind of confining pressure is actually much larger than what we set for the resilient modulus test. Even though we can set using the same procedure, but to prepare the sample, but we need to apply very large confining pressure to the sample. And the failure is defined as the peak pressure of the, sorry, this is a typo here, of the 3 maximum value of the principal stress when principal stress difference reaches, which would be the deviator stress. We will stop the test after the load peaked and then drop it down to about 20%. So what we will observe about the load from the triaxial test will be shown in this figure. The machine will measure the axial strain, which will be the epsilon A from the major principal stress, and then it will also measure the axial load. So we'll actually have 3 different confining pressure applied to the in the test. That is 15 psi, 30 psi, and 45 psi. These three curves shows the maximum shows the result from the three confining stress. Let's just take the first one as one example. So we will keep on increasing the deviator stress or the load to the specimen until going to be failed. And at the point of the failure, you will have the highest deviator stress. That is delta sigma A. And then we're going to reduce the load about 20% and then complete that one round of the test. And next you will prepare the sample again and conduct the test with 30 psi for the confining stress, and then find out the maximum deviator stress, and similarly we'll apply the 45 psi confining stress. So with that, we will have the maximum deviator stress at each confining stress, and then we can use the result to find out to draw the Morse circle, which would be the figure we showed on the right. So to draw the Morse circle, we need two values. Let's just take the circle 1, which would be the result from the confining stress of 15 psi. So in the Morse circle, we have the confining stress defined as the left end, that is sigma 3a. And then for the right end, that will be the maximum principal stress, major principal stress, which will have the sigma 3 sigma 31a equal to sigma 3a plus the delta sigma a. So that's the value which would be the right end of the Morse circle. With these two ends, you can draw the Morse circle, which is in a half circle defined by these 2 points. And similarly, you can find out the value, the Morse circle for the second confining stress 30 psi, and the third one with 45 psi. With these three Morse circles, you should be able to find out the curve which will fit to the tangent to all these three Morse circle, and then you can use this Morse circle to identify the relationship between the shear stress, which would be the vertical axis, and the principal stress sigma. So this is actually in a line, so you can find out the linear relationship. And in this linear relationship, the constant coefficient C will just be the intersection between the line and the y-axis. So this would be the value of C, and C is defined as the cohesion. And also we have the another one, which is 5, and that's just be the slope of this line. So it will show the angle of this line, and we define phi as the friction angle. And these two variables, cohesion and the friction angle, is actually the result that it can capture from the triaxial compression test, and they will be applied to measure the response of the soil to the shear strength. And of course, with a higher cohesion and the friction angle, we will have the stronger resistance to the shear strength. And now I have some questions for you to think about, and I would like to have some open some discussions about these questions. So So for the first question, actually we have 3 questions. For the first question, the value of C and phi generally required in the pavement structure design. And the second one, given the center of the certain density, is the friction angle of the soil constant? And the third, what if the density of the sand is increased? Does the friction angle also increase or not? So we can have some discussion to bring out your thought about the answer, these questions. So you can just using some of your intuitive sense of the materials, like you for example, for the first question, do we need to measure the cohesion and friction angle to design the pavement? Any ideas about it? Okay, I can give you the answer of the first one. So the both variables are very important for the pavement design. They will actually shows how the soil will react to the shear stress. So in the pavement design, we need to consider both the direct load, which would be the principal stress from the traffic. We also need to think about the movement of the traffic, and that will be reflected as the acceleration deceleration behaviors, and it will be represented as the shear stress between the pavement layers. So in that sense, we need to consider the shears, the cohesion, and the friction angle. So the answer is yes for the first one. And for the second one, if the sand has a certain density, is the friction angle generally constant or not? It might be not quite intuitive to get the answer for this one. Usually for the sand, if it has a certain density, means that it will have a certain compaction, and the friction angle for that sand, it's not necessary to be constant. It actually depends on the fine materials the percentage of the fine materials in the soil. Usually with higher fine materials, the friction angle would be smaller. So so we can claim that given sand of the certain density, the friction angle will not necessarily to be constant, and it still be affected by a lot of other factors. And for the last one, if we increase the density of the sand, which means which will usually be reflected as we have stronger compaction to the sand, and in that sense, for the friction angle, what we will usually observe that the friction angle will also increase as they have the stronger the stiffness of the soil will actually be higher, and this kind of stiffness will also help to increase the friction angle to make the soil have the better capability to resist to the shear strength. So that would be the result of the triaxial compression test, and with that we finish all the topics about the soil properties. And start from next lecture, we will introduce the pavement layers, including the subgrade, subbase, and the base layers. And that will be the fundamental structures for us to design the pavement structure. So I guess that will be all about the lecture today. Do you have any questions or concerns? let me know if we have any problems about the task assigned to you. And we will also have this, the first homework assigned maybe tomorrow, and you will have another week to work on the first homework assignment, which will be related to the soil property. Okay. Okay. If you don't have any question, then that will be all about the lecture today. And just feel free to send me email or just leave a message in the meeting chat so that I can give you some feedback about the class. Okay, good. Thank you very much for your time, and I will see you tomorrow. Okay, I'll be all. Enjoy your day and see you